Namaste. Welcome to the second video in the series of videos on interface controller design. In this video, we will examine the design of the hardware interface and software interface. And before that, we will list out the functionality of the interface controller in detail. Once we list out the functionality of the interface controller in detail without any ambiguity, it will simplify the design process of the various components of the interface controller. So before we set about this task, let us just quickly go through the key takeaways from the first video. So in the previous video, we discussed what exactly are interface controllers meant for. So we saw that they are primarily used for bridging processors with different types of peripheral devices and also bus interfaces. Now, why do we need interface controllers in the first place? They are primarily required because the devices and different bus protocols, they have different timings and different data formats. But invariably, in any processor based system or in an SoC, eventually we will have to interface these devices to the processor. But on the processor side, the interface is always standard. You have a data, you have address, and the directional control pins, reset, clock, and so forth. So in order to bridge this mismatch, we require dedicated modules which are called as interface controllers. Now, if you look at the composition of the interface controller, typically they are composed of the host controller, which is concerned with dealing with the processor transactions, the transactions on the processor interface side. And they have the device controller, which takes care of the transactions on the device side. Then, of course, we will have the hardware pins and the software interface registers. So what are the hardware pins composed of? Of course, here I left to add the device pins. So the hardware pins, they will be composed of the processor interfaces, which are standard. As I mentioned, the data, the address, the read write, interrupt, reset, clock, and so forth. And the pins on the device side, which will depend on the device. For instance, if it's a serial device, you will have a single serial pin and a few handshake pins. If it's a parallel device, then there will be a data bus. And if it's a memory-like device, there will be an address bus also. So the device side interface, the hardware interface, will depend on the device that is connected to the interface controller. And as far as the software interface is concerned, it will be consisting of the various registers through which the processor communicates to the interface controller. This part of the design will be elaborated when we take up the design of these components. So they will consist of the control registers, the status register, and the data register. The control registers will be used for configuring the interface for various transactions. The status register will indicate the status of a particular transaction that is initiated by the processor. Has this transaction completed successfully, or was there a failure of the transaction? So that the completion status will be indicated through the status register. And of course, we need data registers because all these transactions are initiated for reading or writing data from or to a device. So data registers are inevitably required. So if the transaction is in terms of single words, only a single register is required, or if a burst transaction is to be carried out, we may require a buffer or a FIFO or something similar. So this sums up the key points that were presented in the first video. Now to take this design process forward, we will take up a case study. Now we will explore the design process further through an illustration of a case study. So we'll spend some time first describing the details of the case study, and once we understand the functionality that we are going to implement as part of the case study, we will identify the blocks to be designed, and we'll also look at how the design can be implemented. So first, let us describe the case study that we are going to use as an illustration for the memory controller design. So as part of this case study, we are going to take up the design of a memory controller. So what exactly is a memory controller? The memory controller acts as a bridge between a host processor and a memory system. So we have a host processor which is interfaced to the memory controllers through a standard processor interface, and the memory controller in turn is interfaced to a memory system through a set of pins which are part of the memory system interface. Now I am describing the device as a memory system rather than a memory, because here we are not talking about a single memory chip. We are rather talking about a memory system consisting of RAMs and cache memories and so forth. The main, the important feature that interests us being that the latency of the memory system is not predictable. If a particular address is available in the local cache memories, then the data may be available in one cycle, or if it is not present, it will take several cycles or maybe hundreds of cycles, which means that we need some kind of handshaking through which the availability of data will be indicated. And to keep matters simple, we will restrict the transactions to just read transaction into a single location. Read into a single location. So in simple language, the memory controller facilitates the read into a single memory location which is initiated by the host microprocessor. And you might be wondering why we can't directly interface the memory system into the host microprocessor. If it were a simple memory, yes, it can be done. But here it's a memory system with a latency which is unpredictable. So it makes sense to delegate all the accesses to this memory to a memory controller. So the idea is the host will initiate the read transaction, and the memory controller will complete this transaction and interrupt the processor when the transaction is complete. So the host initiates a read into a single memory location. the controller facilitates this read by triggering a read on the memory side and notifies the processor on successful completion of the read. So since the read from the memory has a variable latency, there has to be some handshaking between the memory controller and the memory. So we will assume that there is a busy signal from the memory, which the memory asserts when data is available. So using this signal, the controller can determine if the data in a location that is sought by the processor has been made available by the memory. Or in other words, the busy signal when deasserted will indicate the successful completion of a read transaction. So to keep matters simple, we are just assuming that we are supporting only a read from the processor into a single location. In a practical memory controller, different types of reads will be supported. Single read, burst read, and so on and so forth. But here, of course, our objective is not primarily to design a full-fledged memory controller. Our objective is to illustrate interface controller design using the memory controller as an illustration. So I don't want you to get carried away by the intricacies of the operation of these controllers or intricacies of these transactions. That's why I'm deliberately keeping the design, keeping the number of transactions simple, just one transaction. We are just supporting a single read transaction. So this is what the interface controller is required to do. So before we get into the nitty-gritties of the various transactions that take place on the processor side and the memory side, we need to briefly look into how the processor is interfaced to the memory system. So you have the processor or the host, and whenever the host wants to read a memory address, of course, it places the address in the address bus. And we know that the processor will be accessing several devices, out of which the memory that we are concerned with is just one of the devices. And how does the processor distinguish between all these devices? Typically, some of the higher order address bits, let us say we have a 16-bit address. So maybe addresses, I'm just giving you an illustration, maybe addresses A15 and say A14, that the most significant 2 bits of the address will be used for selecting the device. So we have 2 bits in this case. That means we can select 4 devices. Now let us assume that this goes through a decoding logic. The design of the decoding logic is out of the scope of our discussion. And let us also assume that, say, the address 01 is for our memory, the memory that we are interfacing to the controller. So when 01 is received in the address bits A15 and A14, there is a chip select which is meant for our memory, and this chip select will be connected to the memory controller. And when this chip select is asserted, it indicates that the host microprocessor is accessing the memory system that we are considering now. And when it is accompanied by a read signal, of course, it will be accompanied by a read signal in this case because we are assuming that only read transactions are supported. So there will be a read signal also which is coming from the processor that will be interfaced to the memory controller. And when the chip select is combined with the read, the higher order address bits will indicate the address that the processor wants to read. That means in this case, in our example, it refers to a 14-bit address from A13 to A0. So I hope you get the picture. We are using the top 2 bits for identifying one among several devices, and we are assuming that this particular memory that is our concern right now, it is assigned an address 01. So when 01 is received in A15 and A14, the chip select for this memory is asserted, and together with read, the addresses A13 to A0, which is basically a 14-bit address, will indicate the address location that is to be read from the memory. Okay, on the memory side, of course, we will have the memory signals, which will include the busy, which I mentioned, and the data bus and address bus and so forth. We'll examine this later. Now again, coming back to the processor side, the host processor can access the memory controller for different purposes. So what are these purposes? I just mentioned one particular objective, that is a read into the memory system. But this is not the only instance at which the processor accesses the memory controller. Of course, the only way the processor can access the memory controller is through a read transaction. So what are the read transactions possible? Let us list out the different read transactions possible from the processor to the memory controller. So the first transaction will be a read into an address location in the memory system, which we just now discussed. That is, the processor will place the address 01, which is meant for this memory system, and the rest of the address bits will have some address location which the processor desires to access. And of course, this will be the higher order address bits will be translated into the chip select by the decoding logic, and combined with the read, it will signify a read request from the processor into a location in the memory. But this is not the only case where the processor will try to read something from the memory controller. Because let us assume that a transaction has completed, and the completion of the transaction will be indicated by an interrupt from the memory controller. So when a memory transaction has completed, the controller will interrupt the processor. And what will happen then? There will be an interrupt service routine. The interrupt service routine will again initiate a read into the memory controller. Again, please remember that this is also a read transaction, but the target of this read transaction is not a memory location in the memory system. It is a read into the status register. Status register. So why does the processor wants to read the status register? It wants to read the status register to determine whether the transaction that was initiated previously by the processor has completed successfully or not. So by determining whether some specific bits in the status register are set or some other bits are set, the successful completion of the read transaction from the memory system can be determined. So you can see that this also is a read. But it has to be remembered that this is not a read into the memory system. It is rather a read into the status register, which is available locally in the memory controller. So again, how will the decoding logic distinguish the read into the status register from the read into the memory system? Again, this is distinguished through the address. So the address that is placed by the processor for the status register read will be totally different from the address range which is assigned to the memory system. So it has to be remembered that the address or rather the address range for the memory system will be different from the address of the status register of the controller, which typically will be a single address. Of course, it is a memory map system, therefore this address will also be part of the entire memory map. So when this particular dedicated address is accompanied by a read from the processor by assertion of the read signal, it indicates that the processor has not triggered a memory read, it rather wants to read the status register. So the decoding logic is expected to generate the chip select also in this case. In addition, it has another output called the status register, SREG output, which indicates that this read is not meant into a memory location. It is rather meant into the status register, and the memory controller is expected to provide the status register contents through the data bus of the processor. Of course, I have forgotten to show that this is the data bus of the processor. So when the address of the status register is placed by the processor accompanied by a read assertion, it indicates that the status register contents are requested by the processor. Therefore, the decoding logic is expected to assert the chip select and the SREG signal. So this is the second read that can emerge from the processor interface. So we are still not done. There could be a third read. So apart from the read into the memory system and the read into the status register, there could be a third read. What is this read all about? It could be a read into the data register of the controller. So why does the processor want to read the data register of the controller? Because it contains the data read from the memory system in response to a memory read initiated by the processor, memory read initiated by the processor earlier. So the processor had initiated a memory read earlier and it completed successfully, and the data that was fetched from the memory is currently available in the data register. And of course, we have mentioned that the successful completion of the transaction triggers an interrupt. Therefore, the interrupt service routine will first read the status register, and if the status register indicates successful completion of the transaction, then it could be followed by a read into the data register, eventually for retrieving the data that was fetched from the memory system. So therefore, you can see that the memory controller has to support three different types of read from the processor side. Having said this much, now we will proceed to elaborate the various transactions that are part of the functionality of this controller. So as we have seen, there are three possible reads from the processor to the uh, uh, memory controller. So in all these cases, the chip select is asserted and the read signal is asserted. But if it happens to be a register read, the corresponding signal of the register will be asserted, like SREG in the case of the status register and uh, data reg in the case of the uh, data register. So the read into the data register requires a dedicated signal, just like the SREG. It requires a dedicated signal which indicates that the data register is to be read. Let us call the signal as DREG. So having said this much, I think now we are ready to list out the various transactions that describe the functionality of this controller. So let us start from a memory read. So what is a memory read? The memory read is the read of a memory location from the processor, from the host. So how does it get initiated? The first step is the assertion of the chip select. How is it asserted? The chip select is asserted whenever either the status or data register or the memory that is interfaced to this controller is addressed. That means the addresses corresponding to the status register or the data register, or the range of addresses that make up the memory map of the particular memory that is interfaced to this controller, is available in the address bus. So when this happens, the chip select is asserted. It basically indicates that there is some transaction that is initiated by the processor on this particular interface. So along with the chip select, probably after an interval of a clock, the read signal is asserted. In fact, both these signal assertions are part of all the three reads that we have discussed earlier. Now, the address bits that form the address of the memory location to be read. For example, in the previous illustration, we considered that A13 to A0, they are part of the memory location that is to be read. So the address of the location to be read from the memory is available in the lower order address bits. As I mentioned earlier, the higher order address bits may be a few bits, either 2 or 3 bits, depending on the number of peripherals that are interfaced to the processor. The higher order bits are used for selecting a particular peripheral, and the lower order bits actually indicate the actual address location that is to be accessed. In this case, of course, we are supporting only the read access. So the address of the location to be read is available in the lower order address bits. And as the interface controller, what is it supposed to do? The interface controller is supposed to register this address, or capture the address to the internal address register. So the address register is part of the software interface of the interface controller. Therefore, the address that is specified by the processor to be accessed from the memory will be now stored internally in the internal address register. Then what happens? A start is given to the device controller to initiate a read on the memory side. So in an earlier discussion, we have seen that there are two controllers that will be part of the interface controller. One is the host controller FSM, and the other is the device controller FSM. So whenever there is a read transaction to a memory location from the processor, the address will be internally stored in the address register, and a start will be given to the device controller state machine. And this will be an indication for the device controller to initiate a read transaction on the memory side. So as part of this, of course, the address register contents will be connected to the address bus of the memory on the device side, and all the other handshake signals like the read signal and perhaps the chip select signal. All the interface signals on the memory side will be asserted by the device controller, which is a part of the interface controller. And once a transaction is initiated, the device controller waits for a ready indication from the memory. So we are assuming that once the location that is requested from the memory is available, the memory asserts a handshake signal called ready. And as we saw earlier, the latency for the completion of this process is not predictable. It depends on how long the memory takes to fetch a particular location. It depends on the cache, the availability of the location in the cache, or in case of a miss, it has to be fetched from the secondary levels of the memory, and so on and so forth. So once the location that is requested is made available in the data bus of the memory is expected to assert a ready signal. And when the controller sees the ready signal, what is it supposed to do? The controller will capture the memory data bus contents into the internal data register, into the internal data register, and the done bit of the status register is set. Also, the processor is interrupted. This completes the transaction on the memory side. So on successful completion of the transaction, the completion is indicated by setting of the done bit, and in addition to the setting of the done bit, the processor is also notified through the interrupt line. So the processor is interrupted through the interrupt line. Now, of course, the rest of the actions are dependent upon the processor. The interrupt service routine is expected to read the status register to determine whether the transaction has completed, and it is also expected to read the data register to obtain the data that was fetched from the memory, which means that there are two subsidiary uh, set of transactions that are also part of the functionality of the controller. That is the status register read and data register read. And the procedure is more or less similar. So the assertion of the chip select and read, these two events are common to the read of a memory location or the read of a status or data register. But now, apart from this, the control signals differ, because in the case of a memory location, the select signals of the registers, that is SREG or DREG, are not asserted. But when a status register or data register is read by the processor, the corresponding control signal, either the SREG or the data reg, depending on whether the status register or the data register is accessed. So either of these signals will be asserted, depending on whether the status register or data register is accessed by the processor. We have seen that the status register and data register are assigned dedicated addresses in the memory map, and when these addresses are placed in the address bus of the processor, the corresponding select signals, either SREG or DREG, are asserted by the decoding logic. So the assertion of these signals is beyond the scope of the design of the interface controller. Now, when the interface controller sees these signals, what is it expected to do? In case of the status register access, the status register contents are placed on the processor data bus and the done bit is cleared. This is very important because once the processor reads the done bit, if we don't clear the done bit, then the done status will remain stale. So even if the processor initiates a new transaction and reads the status register again to determine completion of the transaction, let us assume that it is not reading the interrupt. It is directly trying to figure out the completion of the transaction through reading the status register. So if it tries to read the status register again, the processor will wrongly interpret the set status of the done bit as completion of the transaction, though it refers to a previous transaction. So it is very important that in case of the status register, when the processor reads the status register, the done bit is cleared. Now, if the data register is selected, then the response is similar. The data register contents are placed on the MUP data bus. This happens in case of the assertion of the D write, whereas this happens in the case of the assertion of the ACE write. So you can see that the read from the processor into the status or data registers are similar, except with the difference that when the status register is read, in addition to placing the contents of the status register on the data bus, the done bit is also cleared. Whereas in the case of the data register, the action, the response of the controller is just limited to placing the data register contents on the data bus. So this pretty much sums up the transactions that are part of the interface controller operation. So we have seen that there are two sets of transaction. The first set of transaction corresponding to the read of a memory location initiated by the processor, and the second set of transaction, which is a kind of subsidiary set of actions, which consists of the read of the internal status register or data register from the processor. So the processor is expected to read the status or data register after the successful completion of a memory access, as indicated by the setting of the done bit and the interrupting of the processor by the interface controller. So with this, we have listed out all the transactions that are part of the interface controller functionality. With this understanding, now we are ready to move on to the hardware design of the interface controller. So that will be the topic of the next video. That's all for now. Thank you.